Good evening and welcome to Tinkering with Atkelar. My day job is holding me back still, so I have to add yet another project from the pile of workshop related stuff. I really hope to have a few days off again soon, so I can finally tackle some of the more different projects. This time I have an analog multimeter on my bench. The model is called Unigor A43. Dave over at EEVblog was not impressed with it, but when I saw it in one of his videos, I finally knew what the model was and I could get one myself. Why? Because this was the exact meter that was used in the school I attended in the early 1990s. It was the meter I learned to measure electricity with. This device marks my transition away from leaking batteries to measuring them. I do feel very nostalgic about it, and while it might not be the ultimate best device of the time, it was certainly not bad either. It seems to have hit the sweet spot in the triangle between pricing, quality and features that made it interesting to schools all around. Coincidentally, this one seems to have spent most of its life in a school too. When I got it, a few months ago, I gave it a good cleaning on the outside. The meter was working as far as I could tell, but now, as I tried to use it a few times, it was acting up. There seems to be some bad contacts in there. It comes with a quick reference on the bottom. Nice! That plate also doubles as a battery cover. This one is not leaking, but the contacts have seen some leakage before. The design is a sandwich of two circuit boards with the function switch on 3 levels. The selection toggle switches are also implemented with the same sliding contacts. The meter features an overload protection, which is a magnetically triggered mechanical master-off switch. Pretty much the exact same principle as the circuit breakers in your distribution panel. But the wires and the coils are not even connected? I guess some students had a go at it to avoid tripping it. I'll reconnect it later. After removing the connections between the board and the meter, I can have a look. Geez, the contacts are not all that shiny anymore. No wonder it's wonky. The cover of the meter has a crack in the corner. Pretty sure the device fell off a desk at some time. but it's in the corner and hardly visible. What irks me more is that the mirror behind the gauge is cracked. I decided to remove it. Can't be that hard, right?
Several days later.
I didn't know that there was glue around that would bond glass to aluminium that well. I had to crack that thing off, one atom at a time. I also never seen such fine glass dust before. It took so long because I couldn't use too much force, or a hammer, because that would have dented the scale or scratched the visible side. Anyhow, as a replacement for the mirror, I picked the shiny aluminium plate I have around. It does have a mirror finish and is less fragile, so that should never have to come off again. Cleaning the contacts took a bit of time. I had to resort to a fiberglass pen. Contact cleaner alone didn't quite cut it. Now the traces are shiny again. The battery terminals are slightly cruddy from the leaked battery. I polished them and gave them a round of nickel plating. The fresh coat didn't take on the original cover, but at least the damage areas are now shiny again. The circuit breaker is next, but here I ran into a problem. The permanent magnet seems to have degraded, and maybe due to my magnetic screwdriver, it now won't hold the switch in the on position. The principle of the breaker is as follows. The permanent magnet on the back end of the iron core is tuned so that it just barely holds on to the spring-loaded switch in the on position. The core has two coils on it, which are wound in opposite directions and fed via two diodes. If at any time there is a large enough voltage connected to either one, the induced magnetic field will weaken the permanent magnet's one and cause the switch to snap into the off position. The mechanical interlock will make sure that it will only stay on if it is held by the magnet again. There is actually a second switch that is activated when the reset button is released. So while you can push the reset button to connect the main one, the secondary switch will only engage after you release it, which might immediately trip the breaker again. Together with the spark gap and the regular fuse, the meter is rather well protected. Only the 10 amp range, which is on its own terminal, is going straight through. No fuse or anything there, just a huge honking shunt resistor. Eventually, I did replace the old magnet with a new tiny neodymium one. I had to tweak it slightly so it wouldn't be too strong. My baseline is that my digital meter can trip it with the diode tester, which seems reasonable. There used to be a notch in the selection switch that prevents it from being turned over directly between voltage and current modes. The little plastic notch was sheared off at some time, and the knob now rotates a full 360 degrees. I drilled a tiny hole and put in a piece of spring wire as a replacement. The main switch for the battery also read over 2 ohms in on state. My stash had one exact replacement, so here we go. All the better power input. Some grease on all the moving parts, except where it might tarnish contacts. Soldering the connections together again. Putting everything together again. I would have loved to do a trial run in the open, but the meter is embedded in the case and the sandwich design doesn't lend itself to run spread out on the desk. connected a lab supply to the battery terminals and gave it a try. Yes! The meter has 5 internal trimmers. I couldn't find a service manual to validate their settings, so I had to follow the traces of the schematic to work out when they were in use. Based on that, I adjusted them to read DC, AC, ohms, kiloohms and nanofarads. The 6th trimmer is the one for the front panel adjustments. There used to be some rubbery washers between the holding brackets of the PCBs and the case, which have since deteriorated. I put in some foam padding, but I need to get some properly sized punches to make round replacements eventually. And here's a quick overview. The meter has a range from 100 millivolts to 1000 volts and 10 microamps to 10 amps, both in AC and DC. The resistance range is from 0.2 ohms to 50 mega ohms. Capacity from 1 nanofarad to 10 microfarad. The capacity range is not that impressive by today's standard, but everything else is pretty much still useful, even to this day. What is probably the biggest downside of an analog meter is that you have to know your positive from your negative. Digital ones will just add a negative sign to the display if you get it wrong. Here, you'll bury the needle. The advertised feature set includes such things as high accuracy, high internal resistance, even for AC, frequency range from 15 Hz to 40 kHz, multiple layers of protection, and such gems as clear, service-friendly build with PCBs and shapely case. Well, if you like bricks, I don't judge. And here we go. Pretty awesome. The measurements are practically spot on, and I can't see any wonky contact anymore. I hope you enjoyed this episode. See you next time! Because that would have dented the scale or scathed the visible side. Darn it, visible side.